So is this from the previous class?
Yeah, correct. I think so.
Okay. So like 2 weeks back there was a subjective test, right?
I think so. Yeah, correct.
So can you send me the question paper for that? I didn't
Mm,
attend it, that's why. Just for practice.
Okay, fine. Okay, let me see where it is actually. It was on haloalkane halorine. I think so. Yeah.
सर ये HNO3 वाला मैंने नहीं लिखा लगता।
कौन सा नहीं लिखा आपने?
HNO3 वाला मैंने
क्यों?
उसका मैंने स्टेटमेंट लिखा, उसके बाद फिर मैंने एग्जांपल के पास में लिख रहा था, फिर आगे बढ़े थे, फिर मैं लिखना भूल गया था, मैं सो
फिर
गया था।
आप
मैं चेक
स्टेटमेंट के
किया तो
हिसाब से
हाँ
हाँ, आप स्टेटमेंट के हिसाब से ही कीजिए उसको, ट्राई करने मतलब
ट्राई
अटेम्प्ट करने की
करना।
कोशिश। स्टेटमेंट लेकिन हमने नहीं लगता है स्टेटमेंट लिखाया था इसका। आई डोंट रिमेम्बर एक्चुअली।
मतलब
हाँ,
कि
लाइक कुछ रिमार्क्स थे उसमें। आई थिंक
हम्म,
यू आर टॉकिंग अबाउट द रिमार्क्स एक्चुअली।
वही।
Adriel, I have sent it to you.
Yes, sir, I got it.
Please send the answers, whatever you have done till now. Josefa and Sahel at least. What happened? Nobody got any answer. Don't have much time. So when we have dilute HNO3, then we are going to do mononitration. That means there will be two different products formed. One is O-nitrophenol and the other one would be P-nitrophenol. If when we use concentrated HNO3, then we are going to do tri-substitution. That means there will be a NO2 group in all the ortho and para positions. We'll have NO2 here, NO2 in the para, and also NO2 in this ortho. When we have Br2 in the presence of CS2, then it is going to do monobromination. But when we have water, it is going to do tribromination. So from here we have non-polar solvent. That is why it is going to do OH, Br plus a para substituted OH and Br. When we have dilute HNO3, then it is going to do mononitration. And this is one of the questions that we did. Exactly the same question yes in the last class. This position is not available for the attack because it is sterically hindered. But there are these two available positions in which the nitro group can be attached. Now, since we are doing mononitration, we'll be forming two different products. We'll have OH and CS3 as it is. Nothing will change here. And one NO2 will attach here, and you'll get another product in which the NO2 will attach on the ortho position of OH. CS3 is here, and we will have NO2 here. Please start revising, guys. This is very bad. You're not answering questions of the last class also. Where did we end the last time? Okay, so we have done coal-based reaction. We'll do the next one, that is the Reamer-Tiemann reaction. Please write. Reamer-Tiemann reaction. Now this is the last reaction of phenol. Please start writing. When phenol is refluxed with chloroform in the presence of aqueous NaOH, at around 340 Kelvin, followed by hydrolysis, an aldehyde is formed. An aldehyde is not formed liquid. An aldehyde is introduced liquid. An aldehyde is introduced at ortho position of phenol. An ortho position of the phenol, leading to formation of salicylaldehyde, leading to formation of salicylaldehyde. So we start with phenol and we treat this with chloroform. Formula for chloroform is CHCl3 in the presence of NaOH. So we have CHCl3 in the presence of NaOH, and here we are going to get OH, and this chloroform, from chloroform we attach here CHCl2. Then once we have aqueous, we have an NaOH already present here. So NaOH will react with the haloalkane part. You can see CHCl2. There are two chlorines, and those two chlorines will be replaced by the two different OH atoms. So we are going to get OH as it is, and this carbon, which has one hydrogen, it is going to get two different hydroxy group, OH and OH. And once we get this hydroxy group, this will be ONA. This also will be ONA because we have this in basic condition. ONA and ONA. Now, this two OH atom, if it is present, and in the first class of alcohols, we have learned that if we have this case when we have two different hydroxy groups attached to the same carbon atom, it is a case of gem diol, then water will leave from here and you will form ONA with CHO, aldehyde. So you'll have carbon atom with a double bond O, and there will be a hydrogen atom like this. Okay. Now further hydrolysis, that means we are going to add H plus in the presence of water. This Na will be replaced by H. OH and CHO. So this is salicylaldehyde. Salicylaldehyde. We'll also look at the mechanism, but write this down first. If you just want to go directly from the phenol, then you'll write the reaction something like this. The first step is CHCl3, the presence of NaOH. Okay, and the second step, also there is some heat. In the second step, we are just adding water in the presence of H plus. That's it. Write this down, then we'll look at mechanism, then you'll understand it more. See, after this, here we have two chlorine atoms. So two chlorine atoms will be replaced by OH atom that we have already seen. When we have RCl and we react this with NaOH, what do we get? We get ROH. So that reaction is happening in this case in the second step. But what is the first reaction, first step? That is mainly important here. Other steps are very much self-explanatory. Mechanism is important. You will also see one of the few intermediates, a very rare intermediate in 12th standard, right? Mechanism. And then we have here, sorry, not 3 hydrogens, we have 3 chlorine atoms and 1 hydrogen. Okay, so if you look at this hydrogen atom will be delta positive, very high delta positive, because all the electrons is being pulled by carbon atom, which is connected to further 3 chlorine atoms. So all of these chlorine atoms will be pulling the electron density, and hydrogen will be very electron positive. OH negative will come from the NaOH and will attack the H plus ion. So H plus ion will leave the electrons here like this, and it is going to form carbon with 3 chlorine atoms, lone pair, and that is why there will be a negative charge. Make a lone pair here, and there will be a negative charge. Now, one of the chlorine and plus H2 will be there, obviously, because this OH negative is attaching on the hydrogen atom. Now, this CCl3 with the carbon ion, it will leave one of the chlorine atoms, and it will form Cl negative plus carbon attached with 2 chlorine atoms, and there is 1 lone pair electron, non-bonded electron. This is known as carbene. This entity is known as carbene. If you look at carbene, this carbene has 2 bonds, that means 4 electrons. 4 plus 2, that means it has only 6 electrons. If it has 6 electrons, that means it is what? It is electron poor. It is not electron rich, even though you can see that there are non-bonding electrons. So, but it is not electron rich. Now, what is going to happen if we have, in the presence of in the presence of NaOH, sodium hydroxide, our phenol will be converted to phenoxide ion, O negative. There will be Na positive here, but we are not writing Na positive here. We just need this O negative in order to understand the mechanism. And that is why I'm not writing the Na positive in this case right here. Okay, so O negative is there. We have double bond, double bond, double bond. So this O negative will come down, and this double bond will go here, right? This double bond will go here. And what you are going to see, that there can be an attack like this when you have carbon and Cl2. This is electron poor, so it needs electrons. So what is going to happen? This benzene ring will attack on this carbon atom. This electron will move in this, right? This electron will move this way. And what you are going to get? We are going to get a benzene ring in which the oxygen atom is double bonded in the benzene ring is double bonded with oxygen. And here we are going to have carbon and 2 chlorine atoms. Carbon and 2 chlorine atoms. Now, each of the carbon atom of benzene ring, it also has a hydrogen. So there will be a hydrogen here. Now, both the electrons are coming from the benzene ring. So that is why this carbon is going to get a negative charge. And once this carbon gets a negative charge, what is it going to do? It is going to attack onto this hydrogen atom. And this hydrogen atom will leave the electrons here, and this pi bond will break, and it will go once again to oxygen atom. So this type of attack happens, and then we are going to get double bond, double bond, double bond. And here we are going to have O negative, plus there will be CHCl2. Okay, so this hydrogen has been abstracted by this carbon atom. Now, once it is formed, the further reactions are very easy. In the presence of NaOH, we can directly write the presence of NaOH. Both these chlorine atoms will be substituted. It will be replaced by C. Here there will be H, and there will be OH whole twice. After OH whole twice, this will automatically get converted to aldehyde with my O negative as O negative only. There is no change here. O negative is as it is, and it is getting converted to CHO. And on further hydrolysis, that means in the presence of H plus and water, it is going to give me back the OH group here. This OH group is back, and this CHO is already here, right? So we are going to get salicylaldehyde. Done, everyone? Yes or no? Please tell me.
No, sir.
Let me know when you're done. Okay. Done, guys? Yes or no? Please tell me.
Yes, sir.
Done. Okay. Now, this is all about the chapter, alcohol and phenols. Now we are going to learn about ethers. Please write the heading ethers. For ethers, you are going to write, please write, first of all, what is ether? Ether will have one oxygen atom, and on the either side of oxygen atom, you will have alkyl groups. Okay, you will have alkyl groups. So the common name of ethyl, these ethers are also like this. We have here ethyl group, and here we have methyl group. So we can write this as ethyl, methyl, ether. Okay, that means what do we have? We have two different alkyl groups around the ether. So ether is, when we write ether, that means we have oxygen atom. Ethyl and methyl means on the either side of oxygen atom, we will have some. On the either side of oxygen atom, we will have some alkyl groups. But the IUPAC name for this will be, you will choose this chain, which is the longest chain. That is going to be your functional group. Sorry, functional group here will be what? E. Then the unsaturation will be AN, and the parent is going to be Eth. And then if you look at the substituent is going to be this substituent here, right? So this substituent is what? Methoxy. Methoxy. And this methoxy is attached on the first carbon atom. And this is the second carbon atom. So the name will be 1-methoxy. 1-methoxy-ethane. Okay. There is something that you must know, that if you have a benzene ring which is attached to oxygen atom and it is further attached to a CH3 group, then this is known as anisole. It has it's the common name, but this common name has been incorporated in the IUPAC and we name it as anisole. You can also write this as methoxybenzene, but it is named generally known as anisole. In your CBSE examinations also, you will be seeing this molecule. It has been written anisole, but the IUPAC name, as per all of the rules, will be methoxybenzene. But you have to focus on this anisole more. Focus on this anisole more. We have already done, if you remember, the IUPAC nomenclature of ethers when we started this chapter, alcohol, phenols, and ethers. Okay, so we'll now look into the method of preparation of ethers. Right here, MOP of ethers. In this way, you'll first write. The number one method is dehydration of alcohols. Dehydration of alcohols. Now, if you remember, we have already seen the dehydration of alcohol. The dehydration of alcohol gives CH3 if you have CH2, OH. Then at higher temperature, it gives me an elimination product. That means if I have H2SO4 and I have a temperature of 443 Kelvin, then it is going to give me CH2 double bond CH2. That means we are going to get alkene. But if I do the same reaction in the same reagent, but we have the temperature that is a bit colder. So we are having same H2SO4, but at this time we are having 413 Kelvin. In this case, what we are going to get this CH2O, CH3, CH2O, and then again there will be CH2, CH3. So it is majorly used to make symmetrical ethers. Okay, so please write here. First point. We'll look at how the mechanism works and all, but please write first of all symmetrical ethers. Symmetrical ethers. What are symmetrical ethers? Symmetrical ethers are ethers that are having same alkyl groups around the oxygen atom. On the both side of oxygen atom, we will have same alkyl group. Unsymmetrical means that we will be having different alkyl groups around the oxygen atom of ether. Symmetrical ethers can be prepared by dehydration of alcohols with concentrated H2SO4 at 413 Kelvin. Now 413, if it is difficult to remember, please remember 414. I think that will be easier. 414. It looks also like ether, right? 4, then in between you have 1, and then we have again 4. So in my 12th standard also, I learned it in this way only, 414 Kelvin rather than 413. And no one will cut your marks if you have just 1 degree here and there with Kelvin scale. Okay. So 414 will also work. There's no much issue. Let us look at the mechanism now. Now, if you look at the mechanism, I will take the mechanism of this molecule, CH3, CH2, OH plus H2SO4 in the presence of 413 Kelvin temperature. It is going to give me CH3, CH2O, CH2, CH3. Okay, that means it is giving me diethyl ether, or we can say it is ethoxyethane. Now, the first step here is in number 1 step. See, from H2SO4 we will have many H plus ion, and those H plus ion will be attacked by the lone pair of alcohol. So we have 1, 2 carbon atoms, 1, 2 carbon atoms, and then this oxygen will have lone pair electrons. These lone pair electrons will attack on the H plus that has been liberated by H2SO4. So we'll get something like this. And this step is known as protonation of alcohol. What is happening to alcohol? Alcohol is getting protonated. So we have H here and we have another H here, right? And this oxygen atom will have 1 lone pair and there will be a positive charge also. There will be a positive charge also. Now in the second step, what is going to happen? Another alcohol group, it will attack here. So you have OH. Now this protonated alcohol, because not all of the alcohol will be protonated at the same time. There will be some alcohol which has been protonated. There will be some alcohol which are not protonated. Now, the ones which are not protonated, what they will do, they will attack onto this carbon atom. Why they are attacking onto this carbon atom? Because this carbon atom, it is attached with oxygen atom, which is having a positive charge. And this oxygen atom, which is having a positive charge, it will attract all of the electrons from the carbon atom, making this carbon very delta positive. So it is highly electropositive, highly electron poor. This carbon is highly electron poor. That is why the oxygen atom is attacking onto this carbon atom, and this bond will break. And what is going to happen after this? We are going to get a carbocation like this. So what is, sorry, no, not carbocation here. It is an SN2. This is an SN2 step. The attack of nucleophile is happening and the leaving group is leaving as it is. So we are having oxygen atom, which already had a hydrogen. And this oxygen atom is getting attached to this 1 carbon atom, and there is another carbon atom. So this oxygen atom will get attached to first carbon atom, and then there is another carbon. So this is the first carbon atom here. This is the second carbon atom. And now this oxygen will get a positive charge because it has 3 bonds. In the last step, there will be dehydration of alcohol. Sorry, deprotonation of alcohol. Third step, please write. Oxygen atom, hydrogen, and positive. So if you see H2SO4, H2SO4 will give you H plus and HSO3 negative. Now, actually, this HSO3 negative, it comes into contact with hydrogen and it abstracts the hydrogen. there can be another another alcohol group which can also attack onto this hydrogen. So there are many ways in which this this hydrogen which is attached on the oxygen atom, it can get detached from this oxygen atom. So this is known as deprotonation, and we will be going to get, this is ethoxyethane plus H plus. So whatever H plus was used in the first step, that is coming back here. So first step is protonation of alcohol. Protonation of alcohol. Second step is attack of nucleophile. Third step is deprotonation. And here the attack of nucleophile, it happens via SN2, and that will give us some points to remember. Okay, so please write these 3 steps in the mechanism: protonation of alcohol, attack of nucleophile, and deprotonation. Let me know when you're done with these 3.
Done, sir.
Okay. Now, write some remarks. Write number 1. The reaction also forms.
So can you scroll up for 1 second? Okay, done.
The reaction also forms some amount of alkene. Okay, so not every reaction is unidirectional. Reactions, there is possibility and probability which is going to be more dominant. So in this case, substitution is dominant, but there will be some amount of alkene via elimination always forming. Okay, now write the next step. This method occurs via SN2 mechanism. This occurs via what? SN2 mechanism. So what is beneficial here? We can only prepare, this is suitable for the preparation of ethers from primary alcohol. This method occurs via SN2 mechanism. Hence, it's suitable for preparation of ethers from primary alcohols. Okay, next is now 2-degree and 3-degree alcohol, they tend to form more, that is in 2-degree and 3-degree alcohol, the alkene, that means elimination is more dominant. Okay, and that is the another reason why this is only suitable for preparation of ethers from primary alcohols. So please write 2-degree and 3-degree alcohols tend to form alkene as major product. Hence, for this method, the alcohol should be unhindered. It should be what? Unhindered. Right? Order of reaction. First of all, we are going to write for dehydration to form ether. The order of reaction for dehydration of alcohol. For dehydration of alcohol, and via dehydration, we form two products. One of them is ether to form ether. And when we form ether, then the order will be 1 degree will be the most suitable, followed by 2 degree, and then followed by 3 degree. And when we are forming alkene, to form alkene, the most suitable is 3 degree, followed by 2 degree, and then followed by 1 degree. Done everyone is on, please tell me.
Just a second.
Okay.
Done, sir.
Right, next. Okay, let us see if we want to make an unsymmetrical alkene, then what is going to happen? So I'm taking an unsymmetrical, if I want to make a unsymmetrical ether, if I want to make an unsymmetrical ether from this method, then what is going to happen? So let us suppose we have this unsymmetrical ether that we want to prepare. So here we have the ethane group and here we have the methyl group. So for this methyl group, what I need to do, I need to have CH3OH. And for ethyl group, I need to have CH3CH2OH, right? And then we need to react this with H plus in the presence of 413 Kelvin, in H plus and 413 Kelvin. Now, and what we are expecting that the CH3O and CH2CH3 will be formed, right? From both of these molecules. But all the methanols that we have, they would not know that in the container we have ethanols also. There will be some methanol molecule that will be surrounded by only methanol molecules. So what will happen? Some of the methanol molecule, they will react with themselves and they will form methoxymethane like this, CH3, OCH3, CH3O, CH3. And similarly, there will be some ethanol molecules that will be surrounded by only ethanol molecules. They will not know whether there is any methanol molecule in the solution or not. So they will react with themselves and they will form methoxyethane that we have seen. And there will be some methanol molecules and some ethanol molecules that would know that there are the other component also. The ethanol molecule will know that there is methanol and the methanol will be knowing that there is ethanol, and it will be forming our desired product, that is CH3, oxygen, and then the 2 carbon atoms. But as you can see that we are forming 3 different ethers, which is going to be a mixture, and this mixture will be very much not suitable for the separation because they will have similar molar masses and similar boiling points. And that is why this method is very discouraged for the preparation of unsymmetrical ethers. Okay, so this method is not used. Please write this method is not suitable for the preparation of unsymmetrical ethers. Unsymmetrical ethers, as it would give mixture of ethers difficult to separate. Done? All of you wrote this? Yes or no, guys?
Yes, sir.
Okay. Now let's move on to the next method of preparation. Okay, fine. Let us do some examples, by the way. You have to make the products, okay? So CS3OH plus H2SO4. What is going to happen at 413 Kelvin? If you have 413 Kelvin, then it is going to make CS3OCS3. Okay, you don't have to figure so much out. Whatever alcohol is given, you just write the R group here. So the general formula will be ROH plus H2SO4 at 413 Kelvin will give you ROR. Okay. Buy the products for these two, maybe. Can have something else. Once you're done, send the answers to me on WhatsApp. Okay, this is also 413 Kelvin. Once you're done, please send the answers to WhatsApp. So I'll receive your answer. Okay. Yeah, fine, correct. All of these questions are no-brainer. I mean, very easy questions. Okay, so we'll be having. I think it's. I mean, Sal, if you were absent, then you need to watch the lecture, right? Yes or no, Sahel?
सर फीस का मसला हुआ था तो फिर पेमेंट करे बाद मेरे को लिंक्स मिल रहे थे रिकॉर्डिंग के
रिकॉर्डिंग के लिंक नहीं रहेंगे तो आप बताइएगा।
जी सर वो बस एक दिन का मसला हुआ था।
नहीं हम वो नहीं बोल रहे हैं। अगर मान लीजिए इस तरह का कुछ हुआ ना तो भी अगर आपको रिकॉर्डिंग चाहिए हम आपको लिंक हमसे आप ले लीजिएगा, ठीक है?
जी सर
ठीक है। I hope all of you have got the same answers as I have drawn here. Okay. Atriel, any doubt here?
No, sir.
No. Okay. Right. Next. Second method of preparation is from alkyl halide. This is very important. from alkyl halide. And it is also known as Williamson's ether synthesis. Williamson's ether synthesis. I will write it sometime as WES. Okay, fine. So what is this? Please write when alkyl halide is treated with. When alkyl halide is treated with a suitable sodium alkoxide, and this sodium alkoxide is prepared by the reaction of Na with alcohol. Okay, prepared by, please write prepared by reaction of Na with sodium with alcohol. Okay, then what happens when alkyl halide is treated with a suitable sodium alkoxide, an SN2 reaction takes place, and SN2 reaction takes place, forming ethers. First of all, we'll make the sodium alkoxide ion. We have ROH plus Na. This is going to give me RONA plus H2. Okay, now this RONA, and there will be some R dash X. So here we have the lone pair electrons. This will attack on the R dash atom, and it is going to give me ROR dash plus NaX. Okay, so please write some examples. We have CS3OH plus, let us say we have CS3CH2I in the presence of NaOH. Okay, this requires some heat also, but it is just like warm temperature, not so much of heat. So if I have something like NaOH and some heat, so first of all, this alcohol will react with NaOH, and then the alkoxide ion will form, and alkoxide ion will react with CH3, CH2I. So what you have to make? You have to just make CH3O, and then remove this iodine, and then you will have CH2CH3. Okay, that's it. So it's a more reaction. If you have ONA plus iodine like this in some heat, what is going to happen? Similarly, what will happen if I have some Br like this, and I have some ONA with some heat, what is going to happen? You can write some more examples. We have here, let us suppose ONA plus Br in some heat, what is going to happen? Write the product for these. Let me know when you are done. Adriel also, please send the answer. Adriel, Huzaifa, Rishan. Yes, sir, correct. These are fine. Very good. Adriel, Huzaifa, waiting for you guys. Correct, fine. So I think these are also no-brainers, right? O, and both of these are symmetrical. We can also make unsymmetrical alkenes. O and 2 carbon atoms like this. Okay, fine. Now there are a few things that we need to know regarding this method. So please write. First point, some remarks. For unsymmetrical alkene, sorry, for unsymmetrical ether. For unsymmetrical ether, it is preferred to have primary alkyl halide. Because 1 degree alkyl halide, are most reactive towards SN2, right? It is more reactive towards SN2, and Williamson ether synthesis occurs via SN2 mechanism. Next point, furthermore, usage of 2 degree or 3 degree alkyl halide, usage of 2 degree or 3 degree alkyl halide may lead to formation of alkene due to high steric hindrance. Okay, so if I have, let us suppose I want to make this product O, and then we have CH3 here, right? So I can either use the alkoxide ion, which is tertiary. So I can either use this alkoxide ion, ONA, plus let us say CH3I, the presence of H plus and 413 Kelvin. No, not 413 Kelvin, some heat. And also no H plus, only some heat, right? The other thing that we can use is, we can use Br plus CH3ONA, right? But when I use this, you can say that when this oxygen atom is going to attack onto this carbon atom, it is quite hindered. So this oxygen atom cannot make way through all the alkyl groups that are attached, and that is why it cannot attack the carbon atom. So what it will do, it will rather attack onto the hydrogen of this carbon atom, which is readily available and which is also acidic in nature. It will attack here, acting as a base. It will act as a base, and this hydrogen will leave the electrons here. This bromine will leave like this, and this will lead to formation of alkene, something like this. And here we are going to have double bond CH2, right? So we have first carbon atom, second carbon atom, third carbon atom. first carbon atom, second carbon atom, third carbon atom. In this fourth carbon atom is having double bond. Plus you will get CH3. Now this oxygen atom has attached with hydrogen, so you'll get OH. This Br will become Br negative and it will attach with Na, so you'll get NaBr. But our main important point is this alkane here. So when we are going to use a hindered haloalkane, then we are going to get what? An alkene rather than ether. So that is why it is preferred to have what? It is preferred to have the haloalkane as 1 degree. Is this clear? Yes or no? Please tell me. Is this clear? Yes or no? Please tell me. You'll write here due to steric hindrance. Alkoxide could not attack. Could not attack on CX bond and rather it acts as a base, acts as a base and forms alkene. Okay. ये सबको समझ में आया कि नहीं आया? Please tell me. Adriel, Sahal, got this? Yes or no?
तो ये सेकंड स्टेप में भी हीट अप्लाइड है.
थोड़ा सा heat applied होगा. That's it. It is just warm, not heat. I mean, you can test the
Okay.
solution. Okay. Right, next. See, if you want to form let us say alkoxybenzene, if I want to form something like this, then it also has two different routes, right? Like this can be prepared by either using Br plus RONA, or it can be used by having phenoxide ion and RBr, right? So here what is going to happen? Here the oxygen atom from here will attack here and will form what? This alkoxybenzene. Here what is going to happen? Here this oxygen atom has to attack onto this carbon atom. And we know that this attack is not possible. Why? This attack is not possible because this is a nucleophile, and nucleophile does not, and this haloarine does not undergo nucleophilic substitution reaction, right? We have learned in haloarine chapter that haloarenes do not go SN at normal temperatures, right? So this reaction is not possible. And this bond is also what? Partial double bond. That is why it will not break in order to form what? In order to form OR. So you can see now, if this bond has to break, the Br has to go away from here in order to form RO bond. Right? The RO bond to attach here, the Br bond has to go. And that is why you will write. Next point, haloarenes and alkoxide cannot be used for the preparation of what? For the preparation of alkoxybenzene. As haloarenes don't undergo SN. That means what is SN? Nucleophilic substitution, and they are less reactive towards nucleophilic substitution. So how will we make alkoxybenzene? We'll write alkoxybenzenes can be prepared by treatment of phenoxide ion with haloalkene. Okay, so we'll write something like this. Br plus RONE, no reaction. But if we have phenol and RPR, then this is going to form OR. Done, everyone? Yes or no, please tell me. So Williamson ether synthesis is a very important topic. Most of the question that has been asked in CBSE from this portion, that is ethers, it has always been from the Williamson ether synthesis. Okay, so we'll do some questions here. Please let me know when you're done. Done, everyone? Yes or no, please tell me.
Yes, sir.
No or yes?
Yes.
Yes. Okay. So see, let me explain the second question first. Okay, we have seen this one just now. Which of the following is an appropriate set of reactant for the preparation of 1-methoxy-4-nitrobenzene? Okay, so first of all, we will make this product. Whenever you see this type of question, you will make the product what they are asking. So we have to make 1-methoxy. Methoxy is OCS3, and in the fourth question we have nitrobenzene, NO2. Now this can be prepared by which of the reactants and why? Okay, so as you can see here, tell me. अभी किया हम लोगों ने सवाल इस तरह का. Just see this nitrogen. See this nitro group is here also. It is here also, right? So whatever. Wait a second. Whatever option you are going to choose, either the first one or the second one, the NO2 is not going to matter, right? Because NO2 is there in both of the options and it is also there in the product. So NO2 is not going to matter. You just need to see the rest of the atom and tell me which is going to be the suitable reagent for the suitable reactant for the preparation of 1-methoxy-4-nitrobenzene. Okay, so you have to see whether we should have haloarine. ठीक है, हम लोग को haloarine चाहिए रहेगा या नहीं चाहिए रहेगा for the preparation of ethers, alkoxybenzene. So we need haloarine or we need ONA. You have just written this. Please tell me in the chat, 1 or 2. In the Zoom chat itself, please tell me which set will be. If you are not understanding, read the last line that you have written about alkoxybenzenes. Yes, correct, Adriel. I'm waiting for Sahel, Huzaifa. I think Rishan is also here. Rishan is not answering. I don't know whether he's here or not. I'm waiting for others.
नहीं समझ में आ रहा सर.
आप फिर से पढ़िए जो भी लिखाया हमने आपको. क्या लिखाया है? Can you read it out? I want to hear you. Sahel.
Okay. Haloarenes and haloalkanes can't be used for preparation of alkoxybenzene, as haloarenes don't undergo SN reactions. Alkoxybenzene can be prepared by treatment of phenoxide ion with haloalkane.
ठीक है, सबसे पहली बात आपको एल्कोक्सी बेंजीन पता है क्या होता है?
Alkoxybenzene होता है जिसमें बेंजीन पे अल्काइल ऑक्सीजन,
बेंजीन पे क्या लगा हुआ?
ऑक्सीजन atom with an alkyl group.
हाँ, तो OR लगा हुआ, right?
Right.
So are we making alkoxybenzene here? Read the question and tell me. Preparation of 1-methoxy 4-nitrobenzene. Is this an example of alkoxybenzene? Do we have this fragment in which benzene is attached to OR?
हाँ, second वाले में.
नहीं, ये प्रोडक्ट्स नहीं, अरे भाई मेरे, हम लोग ये नहीं बना रहे हैं. We are making this product ना. This is the product.
Right.
अब बताइए, इसको बनाइए आप अपने कॉपी में 1-methoxy 4-nitrobenzene और बताइए is this alkoxybenzene, yes or no?
हाँ सर.
ठीक है, अल्कोक्सीबेंजीन के लिए हम लोग क्या यूज करते हैं और क्या नहीं यूज करते हैं बताइए. अभी हम लोगों ने रिमार्क वही पढ़ा ना. टेल मी.
हम लोग for the preparation, right?
For the preparation of alkoxybenzene.
हाँ. So we use RBR.
देखिए RBR किधर है हमारे पास?
RBR we have.
फर्स्ट वाले ऑप्शन में है या सेकंड वाले ऑप्शन में?
फर्स्ट वाले में. नहीं सेकंड. हाँ, सेकंड वाले में.
दोनों चीज पढ़िए ना. RBR के साथ कुछ और भी तो चाहिए होगा. सिर्फ RBR से तो नहीं बनेगा ना. क्या क्या चीज चाहिए हमको alkoxybenzene बनाने के लिए? What are the things that we need? We need RBR, that means haloalkane, and then
and
देखिए one more thing Sahil. Actually use the word that is, for example, haloalkane, because if I am writing RBR, then this R can be anything actually, right? I mean, I may represent it as alkyl group, but it can be also phenyl group, correct?
Right.
So what we should say that we need haloalkane. Yes or no? I think we have written that only.
Right.
So
Haloalkane. So
haloalkane and
haloalkane, and also we need benzene group with ONA, right? So I think second one is the right one.
लेकिन लिखा हुआ भी ना, alkoxybenzene can be prepared by treatment of phenoxide. Phenoxide is what? We have O and this phenoxide. This is sodium phenoxide in total. But if you remove this like this, we remove the Na, it is going to be phenoxide. And
Sodium.
Second, you got it? Yes or no? Tell me.
Yes, sir.
Answer आपके notes में था? Yes or no? Tell
me. Right.
Okay. Then they are asking why. है ना? So why में आप क्या answer कीजिएगा? You will say that haloarenes and alkoxide cannot be used for the preparation of alkoxybenzene, as haloarenes do not undergo SN. बस आई बात समझ में?
जी sir.
Okay, now let us look at the first question here. Okay, let us look at the first question. Write the reaction of Williamson ether synthesis of 2-ethoxy 3-methyl pentane. So we'll write this first of all. So what is the parent carbon chain here? It is pent. So we'll have 1, 2, 3, 4, 5. And this 5 carbon, we have, let me number it also. Here is 1, 2, 3, 4, and 5. So we are having 3-methyl. So here we are having CH3 group. And in the second position, we have 2-ethoxy. We have O, and then we have 1 carbon, and then we have another carbon here. Correct? Now, what they're asking you to make this molecule using Williamson ether synthesis. Okay, Williamson ether synthesis. First of all, let me get all of these molecules in one color. Okay, and then now, whenever you have to prepare anything from Williamson ether synthesis, what you are going to do, you are going to identify the oxygen atom. And then you will see that there is one fragment here. And there is another fragment here. Okay, another fragment here. Now tell me which is the smaller fragment, which is less. I mean, if you look at this carbon atom, look at the carbon atom that are attached to oxygen. This carbon atom is attached to oxygen, the green one. and we have this carbon atom, which is the blue one. Okay, tell me what is the degree of carbon in the green one? क्या degree इसका 1, 2, 3? 1 degree. And what about the blue one?
2.
2 degree, right? Now we also know that when we are using Williamson ether synthesis, one of this alkyl group will be coming from alkoxide ion, and the other will be coming from what? And the other will be coming from the haloalkane. What do you think will be coming from haloalkane? 1 degree wala or 2 degree wala? Which should be coming from haloalkane? 1 degree or 2 degree? Please read the line about unsymmetrical alkene. This is one unsymmetrical. Sorry. Please read the line about unsymmetrical ether. I have this very bad habit of saying unsymmetrical alkene always. So please don't find me. Unsymmetrical ether wala line padi. For unsymmetrical ether, it is preferred to have. It is preferred to have
Primary alkyl halide.
Very good. So tell me here, the alkyl halide will be coming from what? 1 degree or 2 degree? It will be coming from 1 degree or 2 degree, guys. Tell me what happened. अभी तो पढ़ा आप लोगों ने. This fragment here, it will be coming from what? And this fragment will be coming from what? You have 2 fragments, right? The 1 degree fragment and the 2 degree fragment. So this will be coming from alkyl halide or the alkoxide? No idea. Adriel, Sahel.
1
Yes,
degree.
guys. 1 degree. This will be coming from what? Haloalkane or alkyl? Sorry, haloalkane or alkoxide? Haloalkane or alkoxide?
Alkoxide.
1 degree. तो फिर से आप पढ़िए. For unsymmetrical alkene, it is preferred to
for
have.
the 1 degree. Yeah, 1 degree is haloalkane.
It is haloalkane, right? So what is this 1 degree carbon? It is 1 and 2 carbon atoms, and then we'll use some Br group, right? And this whole fragment, it will be coming from alkoxide. Yes or no?
Yes.
So this will be, you will make all of these things, and here you will just make ONA, right? But what they are asking, starting from ethanol and 3-methyl pentanol. Okay. So they are giving you some different reagent. So this what they're asking. So 3-methyl pentanol. This is 3-methyl pentanol. We can make this. This can be made by OH. So you can see now this is 3-methyl pentanol. And if you want to go from here to here, what you need? You just need NaOH, right? And you can also make this bromoethane. If you have here, let us say ethanol. This is ethanol. If you want to go from ethanol to bromoethane, what you can use? You can use simple. Let me write here the same. Wait a second. We get some space. You can go from alcohol to haloalkane using HBr maybe, right? So what we are using? We are using ethanol. And we are using what? 3-methyl. Pentane 2-ol. Okay. समझ में आ रहा कि नहीं आ रहा? आप ये बताइए पहले. This whole idea of how we are going to make this molecule using ethanol and 3-methyl pentanol.
So I don't understand what they mean by starting from ethanol and 3.
So they are saying that you have to start from these molecules actually. From
Okay.
ethanol and 3-methyl pentanol. ठीक है, तो देखिए हम लोग हमेशा starting we are starting from the product and then we are going see products से आपका ये जो wait a second, this ether here, it can be only prepared by Williamson ether synthesis having 1 haloalkane and 1 alkoxide. So first of all what we are going to do, we are going to demystify what is that haloalkane and what is that alkoxide ion, correct? That is my first step. We found the haloalkane and we found the alkoxide ion, correct? Yes or no, tell me.
Yes, sir.
And then once we have got those things, then we are seeing, okay, fine, what is the starting material here? We have ethanol, okay, fine. So ethanol can be prepared by using this haloalkane, right? This haloalkane can be prepared by ethanol also. we will have ethanol, then we will react this with HBr, we will form this haloalkane. And then we have this alkoxide ion, and we have this 3-methylpentanol. So we can say, okay, fine, this alkoxide ion can be prepared by 3-methylpentanol using NaOH. Okay. By the way, this arrow, no, this is retrosynthesis arrow. This means like this fragment can be made by, okay, can be made by, आप इसको translate कर सकते हैं, can be made by. Okay. So what we are writing, haloalkane can be made by alcohol. Okay. We are not specifying any reagents when we write the retrosynthetic arrow. Okay. So our process will be, we have ethanol, HBr, we'll get Br. We have 3-methylpentanol like this. CS3, we'll use NaOH. I have ONA, and here we will have CS3, and then we are going to react these two in order to form O, and here we have CS3. Write this down, let me know when you're done, and then I will start your test. All of you wrote this, yes or no, please tell me.
Yes, sir.
Okay. Fine. See, this is how the mind should work. Okay, actually. ठीक है, जब भी आप ईथर को देखिए ना, तो ईथर में जब भी आप देखें, तो ईथर के आपको दोनों अल्काइल ग्रुप्स दिखने चाहिए. ठीक है, वहां पे आपका फोकस होना चाहिए. फिर उसके बाद आपको देखना चाहिए कि इसमें से छोटा कौन सा है, लाइक 1 डिग्री कौन सा है, वो आपका हालोअल्केन, रेस्ट ऑफ इट विल बी ONA. ओके, एंड देन दिस इज योर द वर्किंग ऑफ द माइंड दैट शुड वर्क, लाइक this is how your mind should work, and this is how you should be representing in the CBSE examination. Okay, chalo, let me give out your question paper. I think it is visible, right? Yes or no?
Yes, sir.
Okay, fine. Also, if you need anything or any help, if you don't understand what the question says, you just speak out, okay? Because I'm like moving away from my laptop, so I cannot see your chats.